In this video, we are going to learn multivariable binary logistic regression. So what is the key concept in multivariable regression? When you have univariable regression and you have only one outcome variable and one exposure variable. And with a multivariable regression, and you have more than one independent variable, and a new variable would be a third variable, and understanding a role of the third variable is very important. So again, we will review the concept of confounding and interaction in the setting we have a binary outcome variable. Example we use is a typical example for confounding concept, which is association between alcohol to lung cancer and smoking being a potential confounding. So we are going to view 2x2 table and later stratified by smoking status. And goal of next few slides are to understand relationship between subgroup analysis with multivariable adjustment. So suppose we are interested in the relationship between lung cancer incidence and heavy alcohol drinking. We conduct a prospective study where drinking status is determined at baseline and the cohort was followed for 10 years. So we have 4,000 patients. And of those, 1,700 are heavy drinker, 2,300 are non-drinkers, non-heavy drinkers. Okay? And 60 patients eventually developed lung cancer. And let's compute relative risk. To compute relative risk, first, which is the same as risk ratio, and the first you do is compute proportion of cancer within a heavy drinker, which is 0.019, and do the same thing for non-drinker, which is 0.0117. Take a ratio between the two proportions, that is relative risk or risk ratio. And today we are learning binary logistic regression, therefore you may want to compute odds ratio instead. So how to compute odds ratio? Odds is number of events to non-events. So let's compute odds of cancer within heavy drinker, which is 33 to 1667, which is 0.0198. And odds of cancer among non-drinker, which is 27 to 2273, so which is 0.01188. Take a ratio of two odds, which is 1.67, the odds ratio. Okay? So when you have 4,000 patients and sample size is pretty large, and odds ratio is meaningfully large, 1.67, so probably p-value would be statistically significant in this case. And based on this 2x2 table analysis, you may conclude alcohol drinking associated with lung cancer. But if you already view my videos in multiple linear regression, you know the importance of assessing this data dividing by the category of smoking. Okay? So that's what we will do next. So this 2x2 table only include 1,000 smokers. So of those 1,000 smokers, 800 are heavy drinkers, so it is 80% of drinkers among smokers. And let's compute odds ratio. 24 to 776, okay, take a ratio. 6 to 194, take a ratio. And then take a ratio of the two ratio. So that gives the odds ratio. And surprisingly, odds ratio is 1.0. It doesn't matter if you put the p-value for this or not. Obviously, there is no association between heavy drinking to lung cancer. If you do the same thing with non-smokers, there are 3,000 non-smokers, and rate of drinking is 30%, which is much lower than rate of drinking among smokers. And let's compute the odds ratio. 9 to 891, the ratio of that. 21 to 20,079, ratio of that, and then again take a ratio of those two ratios, that's odds ratio, and 1.0. So there is no association between heavy drinking to lung cancer. So isn't this surprising? If you analyze data totally ignoring smoking status, we reach statistical significance and may conclude heavy drinking associated with lung cancer. But although, since we doubt there may be confounding by smoking, and we stratified data by smoking status, and we revealed there is no association between heavy drinking to lung cancer. So which do you believe? And of course, by now you know this analysis is unadjusted. Therefore, it is contaminated by confounding. So we can't trust this analysis, right? An association we saw in unadjusted analysis seems clearly biased by higher rate of smokers in drinkers than rate of smokers in non-drinkers. Okay? So let's review conditions for confounding. Confounding occurs when the factor which is causally associating to the outcome, in this case smoking, happen to have association with exposure variable. So here, more smokers in drinkers. So two conditions met, right? The higher percent of cancer in smokers, higher percent of smokers in drinkers. So that's after looking at data separately for smokers and non-smokers, and we found no relationship between lung cancer and drinking status. Okay? In the technical terminology, you can say that after controlling for the confounding variable via stratification, we found no association between lung cancer and drinking status. So we just analyzed, we actually did adjust for smoking confounding by performing stratified analysis. And although we all know disadvantage conducting stratified analysis, that is loss of power. By splitting data, you start losing power. So in this case, smoking specific effect of alcohol is the same in smokers and in non-smokers. So if the story is the same, why don't we combine the result? So how can we combine? That is adjustment. Regression adjustment. So in this case, since there is absolutely no association, so we actually won't gain power at all by combining these two. But technically, I want to show you how you do. Okay, so this is the summary data, and each line include cell frequencies. So first thing we had to let, by the way, dataset name is lung.sav. And first thing we have to let SPSS know is each line include this many patients. Okay, so let's do weighting. Data, weight cases, and frequency, weight by frequencies. And okay, so we're ready to go. And let's skip contingency table because we know how to do analysis using binary logistic regression. So we don't have to get the p-value based on Pearson chi-square or 2x2 table. So let's jump in binary logistic. Okay, so cancer is the outcome and alcohol is our main exposure variable. So if you ignore smoking from this analysis, and what you're going to get is this. Odds ratio is 1.667, which matched with our hand calculation. Alright? And let's perform stratified analysis. To do stratified analysis, go to data, split file. And split data by potential confounding variable, which is smoking. And click OK. And all the analysis you conduct from now on will be conducted separately for smokers and non-smokers. So we go to regression and binary logistic. Okay, and click OK. Alright. So within non-smokers, odds ratio is exactly 1. Okay, and within non-smokers, and odds ratio is again, it's 1. Right? So let's combine these two data and adjust the effect of alcohol for smokers. And how do we do it? And we, unsplit the file because we need data from everybody to do adjustment. And go back. Okay, so here, since we want to adjust for smoking, you stick smoking in. Alright, so by the way, alcohol and smoking are both binary variable, categorical variable. But we didn't worry about clicking this button because it's a binary variable. We called it 0, 1. Okay? Then you don't have to worry about pushing this categorical button. So let's click OK. Alright. So this is exponential b 1.000. This is smoking adjusted effect of alcohol on lung cancer. So this is in fact sample size weighted average between two smoking specific odds ratio. Those are 1 and 1, so average is 1, obviously. Okay, so we're done with explaining confounding. How about interaction? An interaction is a situation when you compute smoking specific odds ratio, and when you see the effect of heavy drinking is different between smoking category, then that indicate potential effect modification, i.e. interaction. So in this case, we have smoking specific odds ratios being the same, which was 1. And although if you see the 1 among non-smokers and among smokers, if you see odds ratio is 3, then that indicate associations between drinking and lung cancer depends on whether you smoke or not. If you smoke and you have a high association. Okay? And when that is the case, you don't want to combine the two analyses. Instead, you want to detect the difference in smoking specific odds ratios of heavy drinking to lung cancer between smokers and non-smokers. This slide summarizes what to do to detect confounding or interaction based on subgroup analysis. Okay, so first, conduct subgroup specific analysis. Okay, within smokers, within non-smokers, examine odds ratio of alcohol on lung cancer. Is 2 odds ratio similar? If it's similar, then you suspect confounding. If it's similar, why don't we pull 2 odds ratios? That is, why don't we adjust effect of alcohol for smoking? Okay, so once you pull, what is the next? You compare the pulled odds ratio, i.e. adjusted odds ratio, to an adjusted odds ratio. And if they are similar, and you may conclude there is no confounding and there was no interaction. And if unadjusted analysis, adjusted analysis is different, you may conclude there is a confounding by smoking. And I go back. When you conduct smoking specific analysis for alcohol drinking to lung cancer, if 2 odds ratios are not similar and suspect interaction, odds ratio of drinking to lung cancer is 3 if you smoke, but if you don't smoke, odds ratio is 1. Okay, so that's a clinically meaningful finding, right? So suspect interaction, and then now you test for interaction. How do you test for interaction? In regression, you include cross product term between smoking and alcohol drinking, right? And check p-value for that cross product term. And if it's significant, report the interaction. Okay? And you also want to report smoking specific odds ratios for alcohol drinking to lung cancer. So that's the procedures. Okay, so using next 3 slides, we are going to exercise this procedure. So here I am showing you 3 2x2 table, and this 2x2 table ignores smoking status. So we are comparing alcohol drinking association to disease, that was lung cancer. Okay, so you have a total of 12 patients, right? And 6 are drinkers and had cancer. 2 are drinkers and non-cancer. 2 are non-drinkers has cancer. And 2 are drinkers, non-drinkers, and didn't have cancer, right? So that's regular 2x2 table. And you compute odds ratio, which is 4.5. Okay? And although if you repeat analysis only within non-smokers, odds ratio become 1. if you repeat the same analysis only within smokers, and odds ratio become 4. So now effective alcohol drinking is clearly different if you smoke, and odds of having cancer is 4 times larger with drinking. But if you don't smoke, odds does not change. Okay, so that's the meaningful difference, right? So then we don't combine these two results. Instead, we try to show difference between these two odds ratio. Then we do test for interaction. Next slide. And here is a same 3 2x2 table. And in this case, when you ignore smoking, alcohol effect to lung cancer, I call it unadjusted, smoking unadjusted odds ratio, was 1. Although, if you look at data differently for smokers and non-smokers, odds ratio become 0.83. And let's look whether two smoking specific odds ratios of alcohol drinking to lung cancer are different. In this case, no, they are not different. And keeping this as subgroup analysis, we lose power. Therefore, since story is the same, regardless they smoke or they don't smoke, so why don't we combine, right? So when you combine, you use logistic regression, okay? And that gives smoking adjusted effect of alcohol, right? Which is sample size average between these two smoking specific odds ratio of drinking. So after you pull, what is the next? So you may want to know whether the smoking actually confound association between drinking to lung cancer. So you compare smoking adjusted odds ratio and smoking unadjusted odds ratio, and let's assume 1 and 0.83 are meaningfully different. Smoking is a confounder. So this slide gives you a situation there is no confounding and no interaction. All right. So let's look at 2 2x2 table. An unadjusted odds ratio is 2. And if you repeat 2x2 table within smokers, within non-smokers, smoking specific odds ratio for drinking is 2 for both smokers and non-smokers. So why don't we pull? So smoking adjusted effect of drinking is 2.0. And compare smoking adjusted effect of drinking odds ratio to smoking unadjusted effect of drinking is 2, which is the same. So in this case, we conclude smoking is not confounding nor effect modification. So this graph is a famous graph called the forest plot, often used when we want to show result of randomized clinical trial to see if the treatment is working in specific subgroup of patients. And this data is from a cohort of women who has breast cancer. And outcome is recurrence of breast cancer. So here, hazard ratio indicate is the time to event analysis. So they use Cox regression and plotting hazard ratio. So hazard ratio of anastrozole is 0.80. So 20% risk reduction by using a new drug compared to standard of drug. Okay? And although if you have positive receptor, hormone receptor, and your risk reduction is even become greater. So hazard ratio is 0.75 in this case. Okay? And compared to women without the hormone receptor, and their hazard ratios are nearly 1. So let's guess if this graph is indicating confounding or interaction. So they did a subgroup analysis, right? And they divide data within women with positive hormone receptor and without hormone receptor, and then compare the effect of drug. So they wanted to see the effect was modified by presence of hormone receptor. So this interaction is, this analysis is to examine interaction. So since two confidence intervals are clearly overlapped, so even though hazard ratios are clinically meaningfully different, and this analysis did not have enough power to show statistical difference between two subgroup specific hazard ratios.